Rest session 10 on generics, function data types, traits, and dynamic vtable. Generic function fundamentally allow abstract parameters and return types for an algorithm that can support a set of data types, similar to C++ templates, but more strict to catch errors at compile time. On compilation, these get turned to non-generic blocks based on types provided at function calls. Now let's try out sample code and then our custom example. So the two calls have an int and tuple being used for same argument, and with a successful compile run. Now let's move on to our example sample. So let's write a generic function find max that will primarily give you the maximum value from a provided vector. As we see here, t is primarily the templating generic variable, and the colon std_cmp partial order is what allows the internal result t to be able to compared, that is like less than, otherwise it won't be able to run that function on it. And where t colon copy allows the result is equal to n, otherwise the generic function definition wouldn't know that it's like you can copy the value. Now let's write the main for it. So we'll have a vector for floating point and we'll like print it. So we'll have the vector available on the screen and then we'll run and print the find max from it. So we'll be able to verify the value. And now let's create a different integer. Let's switch on the values to u32. I'll change the variable name as well. So let's call it L. And let's run it. So as you see, we have a proper same generic function call for float and integer both. Now generic data types, they allow creating custom types like struct of generic nature as well. Benefit being we can have custom types for switching data types in its field by simply having a generic implementation as well. There can be type specific implementations and still allow usage of generic custom types. Now with the example sample for this, so we'll create a struct list that will primarily allow the generic variable to be again comparable, and it'll have a simple field with vector t. And for the implementation of it, we'll have to again provide that t is comparable, and let's implement the constructor for this that will simply return self v. Now we can have find max and find min in it, so let's pull find max from our earlier implementation itself. So let's copy it from here, we'll paste it and clean it up a bit. So since we have already provided the implementation detail, we don't need that, and we'll pass self to it because it already has the vector. So self.0 should provide the vector here. Rest should work. Now let's copy it and write the find min. So let's just switch in the operator for comparison, and we're done for find min. Now let's write the main for it. Again, we'll just create few vectors. So we created a new list. Now we'll just print this list and print the max and min for this. By calling it upon the list variable itself, so find max and find min. Now let's run it quickly. Typos. Let's just go back and quickly fix this. So debug, derive, not driver. Let's see quick println. Now let's try again. Yep, the max and min from the provided vector. Now let's write one more where we'll write a specialized implementation. So struct strings, which will again have a vector with it. What I'm intending is I'll pass strings vector to it and I'll just pop out values for it. So I'll implement specialized for string type, again a constructor, simple self v, and pop. I'll simply get the mutable self and pop out values. So match self 0, that'll be the vector, pop, and if there's a value I'll return that, convert it to string. If none, then empty. So let's write the main bit for it. So string vector, let's just add ABC, DEF, and GHI. Let's have two string. So we're passing the string type, and then strings new. So a mutable strings, because that's what we'll need when we are popping it. So we'll just do 2 pops. Let's just see if it's working fine. So strings.pop, let's run it. Yep, GHI DEF. So that was the generic data type bit, and we did a specialized implementation as well. So now let's move on to generic traits. So traits can well be generic as function in types and get concrete types based on usage. From is a trait. From stdlib, a used commonly variant is string from. Generic traits can have input type based different implementations. Should have only one trait implementation for any input type though. So now let's go ahead and write an example sample for this. So derive debug struct double. That will simply have one field, and we'll implement from on it. So from u8, that'll be, and then for other integer types and floating bit. So this will have a function from, that'll get a from u8, and we'll be returning a double conversion with it. So from into 2, let's just copy it around, F32, and place the same definition there. We can have different definitions in different specializations though. So let's write the main for this. So double for an U8, F32, and I32. So let's do 2, 2.5. I should call the F32 bit, and -2, this should call the I32 bit. I should do 2.0 here because it is multiplying with a floating value. So now let's try this. The result is as intended. We are getting double typed values. Now on to trait bounds. So trait bounds help you expand new traits that a simple generic type can inherit. Like even if you want to copy, clone, debug, or compare particular type, it would need respective traits defined for it. In function definitions can be provided with WhereGuard. So we have already used trait bounds since our first example code. In generic function, t:\stdlib compare partial order allows checking less than, and where t allowed the reassignment in if block. Now point to note is if we already have a generic definition, specialization isn't allowed, as we already mentioned. So now let's write a new example for this, and we'll show how not having particular trait bounds gives us error during compile time. So we have a function logit that's trying to have guard bounds for std format debug and std format display. So when we do :question mark, the debug bit is required. When we just do braces, it requires the display trait. So we'll have println for both, and now write a main for it. And first we'll run it with the proper guards, with proper trait bounds, and later we'll remove them and see what errors we get. So we have passed an int, we have passed a string to it. Let's quickly run it and see. So yep, this is working fine. Let me get rid of the warning. So I'll pass the variable here instead of the value directly. Yep. So now let's do one thing. Remove the display bit, and we'll see we get an error with TSP. So it's showing us clearly that it needs the trait bound for display as well. So let's provide display and remove the debug, so we know that for colon question mark it needs that as well. That's there. So thus, if we are using either of those features, we need those trait bounds to be available for the generic function to work. Now let's move on to the implementation trait. So to associate traits with function arguments and return types, we have implementation trait pattern. Have a bit of different intention when used in either places. With arguments, this defines a trait bound. For return type, it denotes the value must have the given trait. It's more useful to hide exact type in public APIs. So let's write a sample example for this. So we'll have a generic function add one. So currently we are writing without the syntactic sugar. So doing x into would convert the value into integer 32. Let's have a 10 at 10 as well. Here we'll write with syntactic sugar, so we can have the same bit within the parameter, and we could just let it have implement. So implement into 32. Let's just avoid the t colon into 32. Now let's write the main for it. So let's first see how into works. So if we do string from, that means a particular string values dot into would have the same effect. So here x should be equal to y. So let's do a quick print and run. Let's try for add one for 100. Then add 10 for 100, and add 10 for true as well, because should be able to pass in it, and it'll convert it into integer. That should be 1. So we should get, with add 10 we should get 11. Yep. So if we would have passed false instead of true, that would have been 0 when turned into I32. So we would have got just 10. Let's, yeah. Yep, as intended. So let's move on. We'll write an example where the return type has implement trait. So op I1 0 or more, it'll have a random logic to it, but it's hiding the return type, which is showing that the type implements the std format debug trait. So if the provided value, the argument is less than 1, then it'll return a tuple 0 0. If not, then it'll return a tuple with -1 and +1 values. And whatever the value is returned should be able to be debugged mode. So primarily this should work without directly saying that it is returning a tuple blah blah. That works as intended. So now moving on to the dynamic trait. Rust allows dynamic traits, so we get type erased trait object for dynamic dispatch at compile time. As you see in this example, there's a generic bit where a simple implement pet is returned and dynamic pet is returned. So until now we use generic trait that have static dispatch, as in get identified for types required and expanded during a compile time. With dynamic trait, these dynamic objects get dynamic dispatch via virtual method table, vtable. Need an indirection, as with references or even smart pointers like box. We'll see it in our example code. So let's create a new file for this. So we'll create a trait place that should have a travel call and return a string. I will create a struct country and a struct city. Country will have a capital string field and city would have a name string field. Now let's implement place for country. So at runtime, reference to dynamic object is a fat pointer pointing to 2 points. First the dynamic object and second to vtable for trait implementation for that type. So now that we have implemented place for country and city, let's write a generic travel call where we'll simply pass anything that implements place. So this is primarily a static dispatch call. So let's print simply the travel string that gets returned, and after this we'll have a dynamic dispatch call that is dynamic travel. So it's getting an ampersand Dyn place. Now let's write a new place which gets a name and a country and returns a smart pointer box with the dynamic place. So simply if country, then return the country struct within box new and capital as the name. Otherwise simply return city with name field. So let's write the main for it. For country we'll choose India, capital Delhi to a string, and for city we'll choose Brisbane. So let's change the name Brisbane and the field name to name as well. So let's call generic travel first for both India and Brisbane. And we'll call the dynamic travels as well. And let's show the usage of the box dynamic place as well. So we'll create a new place. This will give us the box for this new place. And then let's just print it, US travel. Let's add the semicolons. Let's run and see. Yep, the value is as intended. So now moving on to the exercise generic min. The exercise is simple that needs to implement a generic function to return minimum of 2 arguments. It does require usage of odd trait bounds and ordering enum from stdlib. Ordering enum has less equal greater variance, as in this example calling .cmp returns required variant. Let's run it. It's compiling correctly. So let's create a new file for this. Let's paste in the sample code that's already there, and let's go ahead add println as well, so we'll get some output other than the assert eq. So let's do a min for 110 and a min for 2010. So we should get 1 and 10 in output. Let's implement the generic min function now. So min t, we are implementing it with the trait bound of odd, and then the x colon t and y colon t are the two values that it's getting, and it's returning a t type as well because it's returning one of those values. Now let's do a match on XCMP as you saw in the example from ordering, and %y. This should give us one of three, either less, equal, or greater variance. So that will be, we have already added use std compare ordering. So what we need now is ordering colon less, colon equal, and colon greater. So let's clean this up. So if it's less or equal, we can simply return x. So ordering colon, yeah, and we should return x in this case. If it's greater, we should return y. And this should cover all the cases that could be there. Now let's save it, run it. And yeah, 1 and 10, no assert errors as well. So that was it. Thanks again.